All right. Okay, so what are we expected to do? This is a AC circuit, and we're expected to know the two mesh or loop currents first, and then I might tell you guys to do some specific variable calculation as well. Okay, so the given circuit is in time domain. So let's convert the components in phasor domain. So they're going to change to phasors. Vs will be 15, and frequency does not count here, to an angle of 0 degrees. And let's assume that in this case the units given is volts, and rest of the components are also having the units with them. Okay. Okay, so 15 to an angle of 0, and of course the units will remain the volts. 75 ohms remains 75 ohms. 100 ohms remains 100 ohms. The 0.5 Henry inductor is going to be changed to I times omega, and again we need to see what omega is, so that's your omega. So omega for this whole circuit is 1500 radians per second. Okay. And based on that, you have I omega times the value of the L, which is 0.5. Okay, so that gives you 750, and the units is ohms. Now you have a capacitor, so 1 microfarad capacitor, that's going to be 1 by I omega times the capacitance value, and I have changed microfarads, replace the micro with 10 to the power negative 6 as well. So I goes up, becomes negative, so this gives I 666.67, or just decimal 7 to 1 decimal place. Okay, so now we have all the variables in phasor domain or in frequency domain, and we should be good to solve the circuit. So I'm going to draw the circuit one more time, and we're going to have all the values in phasor form with the variables as well as given numbers. Okay, so let's write down what we have is this is 15 to an angle 0, that was 75, and this is I 750, that's 100. And since all the values are in ohms, so I'm gonna skip writing the units. That was negative I 666.7. Okay, and I'll draw my phasor currents. So this was my current, and I'm gonna say that's I1 phasor. Okay, and that's I2 phasor as well. Okay, so far going good. Let's write the equation now. So let's write KVL at first loop. Loop 1, which is for I1. So we're gonna go clockwise. The first element, we're approaching negative side first, so that's when negative 15 to an angle 0, that's the voltage, so gonna remain as it is. Next element is 75 ohms, so it's a plus 75. And what's the amount of the current flowing through 75 from left to right? It's only I1. Plus, next element is the capacitor, so I'll write its value in brackets, inside the brackets, because it's negative, so I don't want to confuse the negative and positive signs. And the net current coming downwards through this capacitor is I1 minus I2. So two currents you have in here. Okay, so you simplify the equation. It's a 75 minus I 666.7 I1, and plus I 666.7 times I2. Okay, so make sure we are not skipping that I. And the constant term goes to the other side, so 15 to an angle of 0 degrees becomes positive. So let's say this is your equation number 1. Okay, is everybody okay so far? So that's your equation number 1. Did I make any mistake, or looks like we're okay? Yeah, so looks like we're okay. Now the KVL for the second loop. For the second loop, so again, you can start from any component. I'm starting from 750 ohms, and the only current is I2, and that's a plus in here. The next is 100 ohms, is also only current flowing is I2 from top to bottom. The next element is 666.7 ohms, and it's a negative I with it. And the net current, now we're going clockwise for this loop, and this is the most important loop, and we're going from bottom to top. So since we're going from bottom to top, so the current is I2 minus I1 equals to 0. So again, simplifying I1, we have I 0 decimal, no, sorry. No 0 decimal. It's a big number. So 666.7, and it's a negative, negative becomes positive. Okay, so we're fine there. Plus I2 has a couple of terms. 100 is the real part. Imaginary part is I750 positive. Then I666.7 negative. So those are all the terms for I2. And it looks like I have included 1, 2, and 3, all terms. So fine, and the right hand side, there's no constant term involved. So this equals to 0. Okay. All right, so those are the two equations, and now we'll solve those two equations. Solving, I did solve some of them up to the extent to include all these steps. But in this case, let's make sure, no, we did not. So this is our second equation. Leave it up to you guys to practice on. And I'll say the solution. So solving the two equations. Solving 1 and 2. And did we number the second equation? Okay. So solving 1 and 2, the I1 comes as 3.8 times 10 to the power negative 3 to an angle of 46.6 degrees in amperes. And the value of the I2 comes as 19.6 times 10 to the power negative 3 to an angle of negative 83.2 degrees in amperes. So those are the two mesh currents or the loop currents in phasor form. If the question is asking you to put the final results in time domain form, so in that case, I1 in time domain is going to be the amplitude 3.8, and here the units are amperes. Okay, 3.8. You can say 10 to the power negative 3 in here as well, and then it's a cos function, and the frequency we're working on is 1500 T, and the first equation has a positive phase, so plus 46.6 in amperes. You can also skip that 10 to the power negative 3, and you can change the units to milliamperes. So that's also a valid format to write the answer. But both of them are correct unless the question asks you, okay, specify the final answer in milliamperes, then only the challenge arises that the final answer has to be in a specific unit. Otherwise, it's fine. You can leave it in amperes, or you can change it to milliamperes. Okay, similarly, the second current I2 is 19.6 and cos, same frequency of 1500 T, minus this time, because here you have a negative angle, 83.2 degrees. And again, since I skipped 10 to the power negative 3, so this goes to milliamperes. Okay, so that's the three-phase system, and you can see how much you draw, but still you miss something. So AC, and it's a Y delta system. Okay, so you have Y on the source side and delta on the load side. So a three-phase system that has an ideal 240 volts line voltage. Okay, so it's given, the source is given with 240 volts as the line voltage. And in case of Y, we're aware that the line and the phase are different. So line voltage is between any two lines, like between A and a B, between B and a C, between C and a, and the phase voltage is between any line and the neutral. Okay, so this is the line voltage given. You have the delta connected load, and the impedance for the load is given by 90 as the real part and 120 as the imaginary part for each phase. Okay, so this is per phase. Each phase has that value, although I did draw the delta in each phase, and that's the value given. The transmission line impedance, although you can see, but the transmission line impedance is 12 plus I 15N ohms. And the reference phasor we're gonna use A to N as the reference phasor, reference voltage source, meaning reference voltage source means this is going to be with phase angle of 0 degrees. Okay, all right, so let's solve this. What do we need to solve for? So we need to solve for the line currents IA, IB, and IC, and we need to make sure both amplitude and phase. Okay, and then we also have to calculate IAB, IBC, and ICA, and you can see that I have labeled them here. Okay, so these are the currents which we need to calculate, and again both amplitude and phase. Okay, so when we have, first of all, when we have a Y delta system and when we have to solve for it, when we have to analyze it, what we do is we convert the delta connected load into Y. So we convert the delta connected load into a Y connected load. Okay, so in order to do that, the ZY for each phase and Y is given by Z delta divided by 3. And the Z delta is 90 plus I 120. So 3, so that gives you 30 plus I 40 in ohms, and again in each phase. And now for solving it, for analyzing the system, we can make use of per phase equivalent circuit, meaning we'll draw circuit only for one phase. We will solve for one phase like IA, and rest we'll see what we need to do. And one more thing which I need to tell you is this system is following, so it says VAN is the reference voltage phasor. In addition to that, it's using the positive phase sequence. It is using positive phase sequence system. Okay, all right, so let's see per phase equivalent circuit. Okay, so you're gonna have one phase and we're gonna choose to draw for phase A, let's say. So this is how your per phase equivalent circuit will look like. Per phase equivalent circuit will have source from only one phase, phase A. It will have the line impedance for that phase. It will have the load impedance from that phase as well, but only for Y. You cannot do it from Y to delta. Okay, so this is gonna be ZY. This is Z line, and the value was 12, I 15, and the value here was 30 plus I 40 in ohms. Okay, and let's say this is your, now if this is A, this is not B, this is N. Okay, and this is, sorry, uppercase A. Okay, and what we have been told, V, A to N is going to have a phase angle of 0 degrees, but what is its amplitude? That's the question. And we learned in case of Y connection, there is a relationship between the line voltage and the phase voltage. And what is that relationship? V line equals to root 3 times V phase. There's an angle of 30 degrees as well. So here there is an angle of 30 degrees too. But right now we're not considering that. Why not? Because we're going to say whatever the amplitude of V phase comes, which is, let's say I'm going to say this is the amplitude. V line amplitude divided by root 3. So V line was given to us as 240 volt divided by root 3. So whatever the phase value comes, we're gonna write that as it is, saying 240 divided by root 3. But since VAN is we have been advised to use VAN as the reference phasor, so here I'm gonna say this is having an angle of 0 degrees. Okay, so it doesn't matter you consider this 30 here or not. What will matter is when you're gonna relate the, let's say you're writing A to B from here. Okay, so you will say A to B will have an amplitude of 240, but its angle will be with respect to considering AN has an angle of 0. So let's say V phase, AN has an angle of 0, VAB will have an angle of 30 degrees. So that's where it will play its role. But we have been told to use AN as a reference phasor. That's why I have used 0 degrees for AN volts. Okay, so that's your VAN. And the value calculated is 138.56. So this is 138.56 to an angle 0. Okay, and what are we calculating? We're calculating this current in here, IA. Okay, now from this single phase equivalent circuit using Ohm's law, so IA will be given or calculated as VAN divided by the total impedance, and the total impedance includes both the line impedance and the load impedance. So the voltage is 138.56 to an angle 0 divided by the line impedance is 12 plus I15 and the load impedance is 30 plus I40. Okay, so simplifying 138.56 to an angle 0, 12 and 30 is 42 plus I55. Okay, and you need to convert this to rectangular form and sorry, the polar form, and I have the value, so I'll write that down for you guys. So 138.56 to angle 0 and 42 plus I55 in polar form is 69.2 is the amplitude, and the angle is positive, of course, 52.63. This is in volts and this is in ohms, so the value of the IA calculated will be in amperes. So the value calculated for IA, the result comes to an angle negative 52.63 degrees in amperes. Now once we have calculated IA as a phasor in here, you don't need to draw equivalent circuit for phase B, for phase C, and for each phase. What you all need to do is you need to keep in mind we're given the positive phase sequence. Positive phase sequence means it's a A, B, C phase sequence, okay? Means B lags behind A by 120 and C lags behind B by 120. Now, let's say AA is where? A is at angle 52, okay? So that means if B is behind A by 120, so it's going to be 2 to an angle of 52.63, and then you say minus 120, okay? So you don't need to do the entire calculation. You just use the information given that it's a positive phase sequence system. Okay. 63 in degrees and amperes. Same as for phase C. Now for phase C, as let's say here we draw the 4 quadrant space, okay? And I'm gonna draw by A being the base phasor on 0 degrees. That's gonna be a bit easy for us to draw. So let's say here is some phasor A, okay? And here is the phasor B at 120. And this is where the phasor C is going to be. So what I wanted to say, so phasor C is lagging behind B by 120, and it's showing that in that case, since it's a balanced system, so C is also going to be leading A by 120. So what does that mean? Let's say if we apply in here. So C is going to have the same value, amplitude 2, and you can say A, which has a phase angle of 52.63, and you can add 120 in here. Okay, so this is going to give you correct value. So that's going to be the total angle in positive in amperes. Or what else you can do? So IC is going to be 2 to an angle. If you are taking A as the base phasor, so I'm writing C with respect to A. So with respect to A, so that's your A and that's your C. So this angle, this total angle is 240 negative. Okay, so you can also do negative 240. So either one of them, both of them are correct. So 2 to an angle of negative 292.63. Okay, so either you write in this form or you write in this form, they both are correct. So that's the calculation of the line currents. Okay, IA, IB, and IC. Okay, anyone has any questions? So I'm gonna stop here for 30 seconds to see if you guys have any questions. IA, IB, and IC are the line currents. They are not the phase currents. So since they're flowing in the lines, that's how the definition is. They are the line currents. I'll show you guys which ones are the phase quantities, okay? But yes, they are the line currents. Okay, Jordan? So they are the line currents. If they're flowing in the line, they're the line currents. Now what we have is, so here was the line currents flowing, and this time I'm skipping drawing the, what was that, source side. I'll only draw the load side because whatever I needed from the source side, I have that. And I need to draw back the load in the delta form. Why? Because I am asked to calculate some variables in the delta, which I cannot see once I change it to y. So that's why I'm drawing the load in the delta form again. Okay, but now at least I will label whatever I know. So this current is known now. IA is 2 to an angle of negative 52 decimal 63. Okay, and again I'll write just one of them. Similarly, I know this current IB and I know this current IC. And what am I expected to calculate? I am expected to calculate this current IAB in the arrow direction, okay? And this current IBC and this current ICA. And you guys know that once it flows through the winding or through the parts of the load, so they are called the phase currents. They are the phase currents. And in case of delta, there is a relationship between the phase and the line currents. In case of Y, phase and the line currents are same. So in case of delta, line current, let's say IL equals to root 3 times the phase current, and then there is an angle of negative 30 degrees. So here is negative 30 degrees, okay? You can refer back to your notes on Avenue to confirm this. And of course both sides are amperes, so no need to worry about that. So IL is root 3 I phase to an angle of negative 30 degrees. Okay, now when we need to write the specific line current, so I'm gonna say, let's say I'm talking about A. Okay, so IL will change to IA equals to, sorry, equals to root 3. When I'm talking about A, so I'm gonna be talking about phase IAB. So I phase will change to IAB, and this will remain as it is to an angle of 30. Now I know IA, so I'm gonna substitute that to 52.63 equals to root 3 IAB to an angle of negative 30. So I'll be able to calculate IAB. IAB equals to, okay, so 2 divided by root 3 gives you the amplitude, whatever value you calculated it into, and the total angle will be 30 goes up, or you can say this is the subtraction in the polar, this is a division in the polar form, so that's why angles are subtracted. The denominator angle is subtracted. So IAB is 2 over root 3 to an angle of negative 22.63 degrees and in amperes. Same thing for calculating the other two phase currents. So you can say IBC is, you can write the same relationship saying it's IB in here, it's IBC, and IC in here, ICA. Or you can also apply the phase sequence, ABC phase sequence information as well. So let's say we're doing the ABC phase sequence information. So if we are using that, so IBC is for phase B, that's gonna be at negative 120. So gonna be 2 over root 3 to an angle of negative 22.63 and negative 120. Okay, so that gives you 142. Similarly, ICA is 2 by root 3 minus 240. 262 in amperes, and let's do this. Okay, so that's how you calculate the 3 phase currents. Okay, so that's the AC circuit question we're looking to solve. You have a voltage source 2 cos 2T, the resistance 4 ohms, and the resistance 4 ohms, capacitor 0.25 farads, and inductor 2 henries. And what we need to do is we need to calculate the current flowing through the inductor using phasor analysis. Okay, so what are we looking for? The variable of interest is this current. L T. Okay, so let's convert the circuit to phasor domain. So Vs will be 2 to an angle 0, and of course the circuit is running at a frequency of 2 radians per second. 4 ohms remains 4 ohms, 4 ohms remains 4 ohms, so 2 henries will be changed to I times 2 times 2, which is I 4 ohms. 0.25 farads will be changed to 1 over I times 2 times 0.25. Okay, so what is the capacitor changed to? Negative I and 0.5. 1 over 2, 1 over 2, okay, 2. Okay, I 2 ohms. Okay, guys. So this time what I'm going to do is I'm going to erase the original values of the components, and I'm going to just write down the calculated values. Okay. Alright, so what I have is that's negative I2, that's I4, and that's due to an angle of 0 degrees. Okay, so what's the plan? How are we going to calculate the current flowing through the inductor? Yeah, what you guys say? Right, so one possibility is, again, use mesh analysis, maybe the one which we have used in the first example. Another possibility is you can always use the circuit reduction. Okay, so since we have already practiced mesh analysis, so let's use the circuit reduction. So in case of circuit reduction, what my plan is to calculate, to be able to calculate this current in here, the one which is flowing from the source, and it's the same which is going to flow through the 4 ohms. Once I know that, then I might be able to calculate the drop across the 4 ohms, and then I'll say, okay, let me just subtract the drop across the 4 ohms from the source to find the voltage across these two components. Then I'm going to use Ohm's law to find IL by saying voltage divided by the reactance of the inductor. So that's how my plan is. So what is the, let's say I say this is current I. Okay, this is current I. In order to find current I, it will be the source divided by the total impedance at the source. The total impedance will be calculated as series parallel combinations of few things. So you can see at the first level, the capacitor and resistor are in series because they're sharing the same path. Then they're going to be in parallel to the inductor, and then that's going to be further in series with the 4 ohms. That's the equivalent of expression for finding the total impedance. Since 4 ohms and capacitor are in series, so it's going to be summed up, so 4 minus I2 together. This is going to be in parallel to I4, and that has to be summed up to 4 as well. Okay. So whatever the value is calculated, so we're going to do a bit of a simplification, and then at some level I'll say, okay, this is the total value. Okay? So 4 minus I2 in parallel to 4 will be Z1 times Z2 divided by Z1 plus Z2 plus 4 only. So that gives you I16 plus 8, okay, divided by 4 plus I2 and a 4 in here. So now you have 8 plus I16 divided by 4 plus I2. So simplify that, and then you add a 4. And the final value comes to, the total value of the impedance comes to 7.589 in polar form, of course, to an angle of 18.43 degrees. And the units are ohms. So that's your total impedance. Then I'm going to say the current supplied by the source I is given by 2 to an angle 0, the voltage divided by the total impedance. Volts ohms. Okay. So what is the value coming to? 2 divided by 7.589. So this gives you 0.264 maybe to an angle negative 18.43 degrees in amperes. We're going to make sure that we are always writing the units. Okay. Okay, then what? Now, what I'm going to say, let's say I'll see, maybe get rid of this, and I'm going to say here the voltage, I'm saying plus and a minus, and I'm going to say this is voltage VL. Okay. So So I'm gonna apply a small KVL to where? To the left hand side loop. So I'm gonna write a KVL here. Okay. So the KVL will be -2 voltage source plus 4 times I plus VL equals to 0. So let's see what we don't have in here. So I'm gonna say 4 times the I so you can see that the VL is the only variable which is there to solve. Anyone has any questions? So we'll continue going. So you solve, let me confirm, I4, yes. VL, so I assume that you solve for VL in its phasor form. Then I'm gonna say IL, no, it's again in phasor, not in time domain. So then I'm gonna say IL in phasor form is going to be VL divided by the reactance of the capacitor, which was calculated as, for the capacitor, sorry, for the inductor, I4. Let's confirm. So divided by I4, which is 4 to an angle of 90 degrees positive. So this is going to give you IL in phasor form. Then I'm going to say IL in time domain. So here this is going to have an amplitude, have an angle. Okay, so that amplitude will come here as it is, and then I'm going to say cos 2 was the frequency, 2 radians per second, 2t, so plus minus whatever you will have, that phase angle will come here, and the units will remain whatever the units of this are in here. Okay, so since I don't have the calculated value of the VL, so I'll leave this up to you guys to solve for VL, solve for IL, and then plug in the missing numbers in these blanks.